Dumb thing. Okay. All right. We're gonna jump into regression screening stuff today. And honestly, I feel like this is maybe the first like big kid lecture of the year in terms of starting to get into. I mean, we've got into nuts and bolts and stuff like that. This is starting to get into like under the dash stuff with our tools, right? This is starting to get into assumptions. And, you know, when we last semester doing like means based analysis, stuff like that, important, kind of the bread and butter of psychological research, but a pretty simplistic sort of concept and things along. There's complexities just in terms of null hypothesis testing, understand what's going on, but there's not many moving parts. When we start to get into regression, these are really flexible tools that serve as the basis for our generalized linear models, but they start to come with more assumptions. And as soon as we start violating those assumptions, it starts to degrade the inferences that we can draw from this. Okay. Now you might say, like, well, I don't know, I'm just going to stick it in SPSS, whatever SPSS tells me that I'm just going to run with. Fine, you can do that, but then also you can have models that break down things that don't work when you think that they should. Knowing what's going on under the hood can be really useful for trying to figure out like what went sideways with this. This should work out and it's not. Sometimes it's because you got screwy cases that you might not necessarily notice on the front end, or you've got variables that aren't acting in the way that maybe you anticipated that they would. If you know how to go through screen and look for your data, I can't tell you the number of projects and that doesn't make sense. I've got a finding that I suppose I could get really jazzed about and say, oh, I found something new, like a eureka thing, but I don't trust this. It's not consistent with theory. Is not how this should work. What's going on? And if you get under the hood, start looking, now you've got like 2 or 3 cases that are completely driving a really novel effect. It's not a novel effect, it's an artifact of a violation of assumptions, things like that, particularly when we get into interactions, moderation types of analyses and stuff like that. And so gonna spend some time going through wanting to be comfortable and knowing what should be going on with these models and how to identify when it's not, and then think about the consequences of some of that stuff. Sometimes I violated an assumption and it's not a big deal, or it's not a big deal, but it's things I can at least live with, and sometimes it's not. So we're going to get into some of this. A lot of this is also going to be review. Okay, we're going to talk about screening. A lot of the screening is the same stuff we've done before. So we're going to clip through that pretty quickly, but just want to hit on the high points to make sure that we're on the same page as a refresher. But slow me down if you're like, hey, you've been like taking points off my problem sets all semester for sort of this thing. Help me understand. Want to make sure that you're on the same page with stuff. Okay. All right, so we're going to go through general screening with our observed variables, and we're going to talk about regression assumptions, and then we're going to get into regression screening, which is going to involve primarily looking at our observed variables, but also our residuals. Okay, when we get into regression, most of your assumptions are about your residuals. Okay, and we'll talk about kind of teasing out what that's going to look like. Okay. So just on the front end, why do we go through and screen our data? Why do we care? One, it's just responsible sort of best practices science. Okay. We have tools that are set up to work, right, under certain circumstances, right? And if those circumstances are present, we can draw very strong inferences from these analyses. But if those conditions aren't present, now all of a sudden we start to need to be thinking about like, what can I infer from this and what can't I, right? What are the things? Now, sometimes there are things, if I violate certain assumptions or certain things happen, it's going to push my results one way or the other. I can kind of deal with that because I at least know like, hey, given the pattern of data, this is going to make my results more conservative or more liberal. And then I can kind of make some adjustments in my inferences. But a lot of times it's not. Like, I don't know, like things are sideways and it can do all sorts of bad stuff, right? And now all of a sudden I can't be confident in the assumptions that are the inferences that I'm making from these data, right? Here's a tool, it works well under these conditions if you use it this way. If I start using a screwdriver as a hammer, all of a sudden things get kind of sideways, right? So we're wanting to go through and see sort of how close are we to the assumptions of our model, okay? Equally important, I would argue, providing us with nuances to our, with respect to our data, okay? Um, I go through, I have a project, Charlotte, you and I are talking about like, hey, maybe we go through and do this. This would be interesting to look like. Good in theory. Let's actually collect some data and see what's going on. Are the data doing what we would expect them to do? Are we getting weird stuff that we hadn't anticipated? Here's a measure back. Oh, we'll give this person these measures, but when I actually data starts to roll in, I've got a ceiling effect or a floor effect, right? Like I've selected something that doesn't actually work out the way I would expect it. If you're not looking at your data and doing screening stuff, you don't recognize that everything's on the floor, everything's sort of high above, or like there's weird stuff going on, right? Anytime you go through and step into a defense meeting, you should be in such a position of power relative to us on your committee in terms of knowing what your data look like, what they're doing. If you've done a good job of screening, I'm like, oh, okay, well, I don't know. So you got sort of really getting the full range of things. You're like, nope. If I go through and I look at this, I actually have scores across the whole spread of things. Toward the end, it gets a little bit sparse about at this level. You just flexed on me in there, right? I was like, what about this? You're like, no, I've got this and more, right? Say something again, right? Like if you've gone through and you know what your data are doing, right? It puts you in a really good position, okay? And then also think about development of continuing research, right? Think about what's the next important relevant question. Catherine, you're going through, you're doing a study, you're like, okay, here's what we did, but I'm actually looking at my data. Here's who we're not getting, or we're not getting responses in this area, or we didn't have real good coverage in this cell. This is maybe important because of this thing, right? Um, or you're going through and you're saying, yeah, everybody's using this paradigm, everybody's using this study, but we've actually looked at the data, we've got some limitations on this. We're not capturing this piece of things, or when we're doing it, it's not actually getting at the thing that maybe you necessarily would like to get at. Like all of this is stuff that can come up at screen. This will take the vast majority of your time. Okay. Running your analysis is easy peasy. Doing this is hard, and thinking about like, what am I seeing? What am I getting out of this? What does it mean? That's what's going to open up sort of new ideas, interesting insights, sort of good discussions, things along those lines. The other thing that also makes this difficult is there are no straightforward, like I can't give you, these are the rules, right? If this happens, then this happens, right? I can say, if this looks kind of like this, then you should maybe think about these things, right? But there's no bright line in any of this where like, if I'm like right here, if it's under this value, then I'm cool. And then if it's over this value, then everything's a mess. It's all a dimension, right? You got to think about context. You got to think about your measure. You got to think about your research question. Sometimes it's things that you're seeing in your data. You're like, that makes sense given what I would expect. That's good. It doesn't necessarily mean that your model's fine. It just means that you kind of know what's going on in your data and why, and then you can make some adjustments based on that. Okay. So again, all of this ends up being really, really high level under the hood stuff, but starts to become critical with our more advanced models. Not just knowing like, hey, I did process model 14, right? That doesn't cut it, right? Like, what did you do? What does your data look like? Does that model make sense? And then what started to get screwy on stuff? Okay. Um, a good example here. This is a classic quartet of data. And so what we see here is if we go through when we run a regression model through each one of these sets of data, we get the exact same regression line on each one of these. Okay. Obviously, if you're looking at this, these are very, 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 very different patterns of data. But if I just run my regression is saying the exact same thing across all of these, right? Now, if I'm going through and I'm screening this, right, then I can see like, yeah, like this is fine. That's not fine. Jack, what's going on there? What's the problem that happened with in this panel?
It seems to be peaking and then kind of coming down pretty
Yeah, I got a clear non-linearity in that, right? A linear model is not appropriate for those data. I can run one and it gives me a regression slope that's reasonable, telling me that there's a relation between X and Y, and there is a relation between X and Y. The relationship between X and Y is one. It's causal here, right? It's just my regression model didn't capture that, right? So here I've got a problem with specification because I'm specifying a linear model as something that's nonlinear. That needs to be addressed. Okay. William, what's happening right here?
You have like one outlier that's sort of altering the best fit line.
Yeah, I've got an influence point. Is it ruining my model?
No, but it's probably making you overestimate it'd probably make you overestimate your effort.
Maybe overestimate a little bit and like, who the hell is that? What's going on with this, right? One, it's an error or someone who's screwing around or an RA didn't enter something right or something along those lines. And it's degrading my model fit, so we get rid of it. Or if we're in clinical land, maybe this is someone who is this? What's going on? I've got a model that fits perfectly, everybody else, then I got one person who it doesn't, right? Is there something unique going on about that person that then leads me to think like, hey, we got a model that kicks ass for all of sort of this group, but then we got a group of folks and it doesn't fit well for. What's going on there? What's different in terms of the experience of sort of whatever I'm looking at in this area? That's a new direction that we might start to go through and take a look at because I was careful in looking at my data. Okay, Catherine, what's happening right here?
Most everyone has the same X value except for one person is an outlier.
Yeah, you basically my predictor variable is basically a constant, and then someone else just happened to be out there, and then it sort of created a regression line, right? Really, it looks to me like probably there's no relation between X and Y. Although I didn't get any variation in X, that should also be a problem, right? Huge red flags, right? But if I'm just going through and saying like, hey, look at regress Y onto X, who knows, right? So again, an example of why it starts to become so important to take a look, see what your data are doing, and saying, does this model make sense given what I'm seeing in my data? Okay. And again, so just knowing sort of what you're doing and just learning this stuff at a very, very deep level, sort of giving a good consideration of what's happening, and then starting to get an appreciation of sort of whatever phenomenon it is that you're looking at, just really have an impact up front. Like you are developing expertise in these measures and these assessments and what they do when you put them together with stuff. Okay. So when we're going through and thinking about for this class, thinking about screening, we're going to step through same process that we did last time. First thing we're going to think about is accuracy, plausibility. Okay. Are our data within range? Right. So here's my measure. It goes from this to this, making sure that everything's in balance, right? Did I code my variables appropriately, making sure that I've appropriately labeled my my categorical variables so everybody's in the right group. I know what is what. Do I have the right number of cases? As you go through and you work collaboratively with people, you will get data sets that are a goddamn mess, and it's such a headache to go through and deal with, right? Like sort of good data management, making sure that things are labeled, right? If they look good to you, that's one thing, but if you pass that along to anybody else and no one can decipher what the hell is going on, I think sort of a good example of this, and this isn't necessarily this, is I sort of when I started senior person in my lab was Icelandic. And I got a bunch of syntax files from Berglund, and they're all in Icelandic. It's like I don't know sort of what's going on with stuff. That's a language thing, but sort of making sure that sort of you've gone through, and if you needed to pass a data set along to your advisor or anybody else that they could go through and navigate that set. Also, variable names that make sense to you right now, and things that you sort of make sense to you. Remember what you did right now. Give that 2 months and you're going to have completely forgot about what the hell you did or why you added or dropped people, things like that. Having good records on this is going to be really, really critical for solid data collection. Okay. So here we're just looking at means, standard deviations, or sort of, excuse me, frequencies, descriptive statistics, just to make sure that everything's in balance. We also want to be thinking about missingness. So we're going to start to go through and think a little bit more carefully about missingness. This is a whole area of quantitative science about mechanisms of missingness and what we do and sort of the implications of this. What we know is that certainly we want to make, and so last semester we were focusing on like how many cases are missing, and then remember sort of wanting to, for that group-based analysis, like, okay, if cases are missing data, tell me what group they're in. Right? Like, are they in sort of this group or that group or this condition, that condition? What we're getting at with that early on is thinking a certain thing about patterns of missingness. Okay, what's the mechanism of missingness? Kitty, if you got, some missing data and it's kind of spread across, your 3 different conditions and it doesn't look like there's anything really systematic going on there, probably not too much to worry about, right? But if you've got missingness only in condition 3, condition 1 and 2 are pretty. I'm starting to worry that there's something systematic going on in condition 3 that I need to be thinking about carefully. Okay. As we're going through thinking about mechanisms of missingness, if you've got truly random data, truly random missingness, we can often talk about this as ignorable because it's just a random function. There's nothing that's driving missingness anywhere. And then you're just losing people, right? It's not great for, sort of it decreases your power to the extent that it's reducing your N, but there's not anything too concerning there. If I have non-random missingness, this can start to impact your inferences, generalizability, things along these lines. There is a paper that I've assigned that I need you to read carefully. I also posted this Schaefer and Graham like a handout on that. I want you to know this stuff well. Okay, what this is doing is it's introducing sort of a taxonomy of missingness where you can start to think about potential consequences for your data. At the top of that taxonomy is a missingness mechanism that we would call missing completely at random. Okay, missing completely at random is basically what we would normally think about as missing at random. Okay, it's meaning that the probability of whether or not your outcome variable is there, whether or not Y is present or absent, is independent of all other variables in the set, including the variable itself, right? So William, if you're looking at sort of volume of alcohol that people are reporting drinking, if people that didn't reply to that or didn't respond to that, if that's missing your data, the true value that's missing there is not related to any other variable in your set. It's not related to sex, college status, family history. So like it's unrelated to that. And it's also unrelated to the actual level of missingness or the actual level of drink that's going on. This is just a random process. Okay. So this is pretty easy. MCART, this is ignorable. Okay. You also have within the Schaefer and Graham system something that's known as missing at random. Okay, this starts to become more important when we get into some regression-based analyses, things like SEM and things along these lines, where we have missingness, and that missingness is not random as we would think about it sort of colloquially, right? There is a reason or a probability that some data are missing, where we have the presence or absence of some outcome variable Y is dependent on observed values of X or some other value of X. Okay. Here's what's going on is if I've got data and let's say, William, we'll go back to you. You're asking people how much they drink. Okay. But what we find is you got a lot of missing data in there. And let's say you're recruiting through Aware or something along those lines or things along those. So there's some mechanism right there. And what we start to see is that people with missing data tend to be underage. And maybe they tend to be people who have higher religious affiliation, right? Which starts to make sense to me, right? So the people who are underage and not want to report on themselves because they might be afraid they're going to get sort of in trouble, or sort of maybe they have sort of religious things that they're going through and underreporting. That's not missing at random, right? That missingness is dependent on some things that you've gone through and collected, but we've also collected sort of information on that. So I do know what people's ages are, and I do know religious affiliation. And so long as those variables are in my model, once I account for age, once I account for religious affiliation, after we pull that out, anything else that's left over that's missing is just kind of random and sort of floating around. That's missing at random. Okay. Basically, there's a mechanism of missingness to my data, but I know what it is and I have variables to account for that. Okay. If I've got this situation, I'm still ignorable, right? I can run maximum likelihood estimation without bias, right? Because yes, I have missing data. There is some systematic pieces to this, but the things that are driving the missingness are things that I've already modeled in my data set or in my model. And so as a consequence of that, once I account for those variables, anything that's left over is kind of random. People see the difference between MCAR and MAR. Last classification is missing not at random. Okay. Here, what we have is we have the probability or presence of absence of value of your outcome is dependent on the true value, right? Like, so here you've got people who are drinking more, tend to not report that they're drinking more, right? So we've got missingness that's depending on the thing that I'm measuring, and also probably a function of some predictor values as well, right? So my missingness tends to be, and I don't know this because I don't have information on their drinking, but if people who are using more are the ones who tend to not report, and then also maybe that tends to be a function of, let's say, sex, where women are underreporting more than men, but I didn't include sex in my model. I got a whole hot mess here that's going to ruin everything. I can't draw reasonable inferences from my data because what I'm doing is I'm missing stuff here. Okay, here we've got missing not at random. My own personal soapbox on this sort of situation here, right? And this is sort of get a little sneak into sort of clinical land stuff like that, right? We have multi-level modeling and things along those lines that are often used for treatment outcome data. And so the benefit of multi-level modeling is that if we're looking at a maximum likelihood estimator, it accounts for missingness, right? Like I can still include people if someone is in my treatment program and so they're in session 1, 2, 3, and then they drop out after that, right? Before, what we would do with our standard models is we would have to just limit it to the people we had data for, or we'd carry last observation forward, things along those lines, right? But we have tools now with multi-level modeling where we can still include those people even though we don't have complete data on them, right? Which is a good thing, right? And it is standard what everybody does. The problem is that estimator assumes that we are at least missing at random, okay? Now, is dropping from treatment a random thing that people do, just like people just randomly decide to complete treatment or not? No. Do we have a good way of predicting who's going to complete treatment or not? No. Do people who drop treatment sort of maybe have sort of their symptom levels have something to do with whether or not they complete or not? Probably, right? So what we're doing with all of these treatment analyses is we're working under the assumption that our mechanism of missingness is missing at random. Well, that's ridiculous. It's for sure not missing at random, right? So what happens from a statistical standpoint is all of that literature is suspect because basically what we're doing is we're taking and looking at outcomes for my intervention. And we're including people who didn't complete the intervention, but the basis for estimating how those people would have been in intervention if they would have stayed in intervention is based on data for people who did complete, which is an apples and oranges thing, right? And so who wants to hear about this? But like it is a thing that, and like I'm not sort of saying that sort of like I've had sort of arguments with sort of reviewers about sort of pros and cons of stuff, and like I'm not necessarily needing anybody to fall on their sword for stuff, but it is something that we should be thinking about. Like, yeah, here's my projected outputs for this treatment, and this is based on everybody who completed. If we're running evidence-based treatments for stuff, we've got dropout rates at 20%. That's 20% of the sample that we're just assuming is going to follow the same trajectory as the people who completed. There's no basis for expecting that to be a real thing, right? So again, wanting to think carefully about what our tools are doing and what the assumptions are doing, even though they're inconvenient sometimes, and thinking about like, yes, and, right? Cool, this is, but there may be, if I'm thinking about this as sort of, I might not have the effects in reality that I actually have because everybody who didn't complete, I'm using data for people who did complete to model their likely trajectory when there's no basis that I can see for sort of thinking that that's would be a reasonable thing to do, right? So again, this piece of things starts to become important. So I've got sort of a missing data sheet work handout to this Switzer and Roth, this Tabachik and Fidel chapter, sort of just go through. This is a really, really important concept. So make sure that you're going through and taking this. Now, in actual fact, like when you're actually running your screening, really tough to go through. I mean, there are like MCAR tests and stuff like that that I don't know are actually really all that helpful. People will report them, sort of more just a report thing, but like sort of this is again when you're looking at your data, something that you have to look carefully, like where's my missingness going? Am I seeing patterns? Are there reasons to believe that I might have systematic missingness? And then think carefully about what that means for your analysis results, inference, and things along those lines. All right, this is kind of a heady kind of topic, right? So like think about like missingness based on what the value would be if it were there when it's not, type of thing. But any questions about sort of this general sort of understanding at least the basics of the framework here? All right, cool. All right. Going to talk about distributional assumptions. Again, univariate normality. This is just talking about our scores reasonably approximating a normal distribution. It doesn't have to be sort of perfect, right? And we go through and we look at that using our histograms and box plots and things along those lines. But then when we get into multivariate analysis, we need to start thinking about multivariate normality. And we talked about this a little bit before in the first lecture. If I'm talking about multivariate normality, I'm saying that each variable and all possible combinations of variables are normally distributed. Okay. Multivariate normality is an extension of that bivariate normal distribution that we had talked about previously into multivariate analysis. And this is really, really, really difficult to test directly. Okay. In bivariate space, right, we're saying that all my data, I can assume my data are bivariate normal if all marginal distributions are normal. That means sort of my x's and my x and my y. If I plot out a histogram, looks reasonably normal. And then I have also evidence of conditional assumptions for every value of x, y has a normal distribution. For every discrete value of y, corresponding x's have a normal distribution, right? We talked about kind of sort of this in terms of bivariate normal space. Okay. And most of our univariate, multivariate tests assume to have some robustness to violations of normality. But this is starting to become called into question, right? Again, it's nice to just say like, well, it's a thing that we need to think about, but it's probably fine if we violate it. Some data suggesting for simulation stuff that may not necessarily be the case, okay? So we always want to go through and do this. Now, I can't tell you, like, there are tests for multivariate normality that have strengths and weaknesses and stuff like that. And those generally sort of those you'll access within SEM programs like M+ and things along those lines. For your day-to-day regressions and things along those lines, these are difficult again to have a test directly for. But what we'll talk about is here are the things, if I go through and I look at this and these conditions are met, I can reasonably assume that my data are at least somewhere in the vicinity of multivariate normality. So again, we're interested here not only in our marginal distributions, but our conditional distributions of a variable sort of paired with at sort of individual levels of my other variable. Okay. When we're thinking about multivariate normality, so this is going to start looking a little bit different if we're talking about grouped versus ungrouped data. Okay. For ungrouped data, there's going to be any continuous regression, other things along those lines. Something where I haven't modeled this now. Remember that a t-test is just a special case of regression. ANOVA is just a special case of regression, right? There's nothing that we did last semester that we can't pretty quickly run in a regression model, right? But those tools are doing things a little bit differently. And we'll talk about that. For ungrouped data, if we're using continuous responses, right? William, you had asked a question sort of about like dichotomizing sort of variables and stuff like that, right? This is saying this would be, I'm not gonna sort of chop something or median split something. We're just gonna sort of treat this as a true continuum, go through and take a look at it. What we would want here to see is if each variable follows a normal distribution, assuming it's a continuous variable, has reasonable normality, and our bivariate relations are linear and homoscedastic, we can assume that this set of variables are then something close to multivariate normal. We're sort of in an okay space here. And we'll talk about what linear and homoscedastic is, what that looks like. Okay. Remember though, for grouped data, our normality assumption is going to involve the distribution of the sample, the distribution of the sample means, not the actual variables. If I'm running t-tests, if I'm running ANOVAs, things along those lines, right? I want to go through and I want to check normality in my data just because I want to see what it's doing. I want to see what the distributions are. I want to make sure that I don't have any weird cases hanging out anywhere. But I don't need the picture that I'm looking at to be normal with grouped data because my assumption of normality involves the distribution of sample means. Okay. Catherine, do you remember under what conditions does the distribution of sample means start to become normal?
Sample size increases if the population is normally distributed.
Exactly. So as long as I got decent cell sizes, as long as or whatever I'm sampling from is probably has a sort of reasonably normal distribution, I'm okay, right? So I start to get less worried about the actual histogram I'm looking at and more so about some of these methods factors. Okay. Not necessarily the case with our regression models. Okay. Questions about distributional assumptions, and we'll get into this, what this looks like more in regression sort of a little bit later on, but in terms of just general overview, feeling comfortable? Yeah, Catherine.
Did you say again what the ungrouped versus group data is?
Yeah, grouped data is gonna be like t-tests, ANOVAs, sort of things. Everything we did last semester, that's all group-based analysis. Stuff that we're gonna do this semester, outside of repeated measures, ANOVA, like this is sort of, these are gonna be ungrouped sort of continuous analyses. All right. In terms of thinking about distributions, right? We've got mean is the first population moment, standard deviation is second population moment. Skew, this is your third population moment, and this is describing symmetry. Okay. Positive skew, we got tail extending higher values, negative skew, lower values. So a problem here is from a means-based standpoint is that our mean is no longer our best measure of central tendency in a skew distribution, right? We got that mean is going to be drug out towards the tail. The mode is going to get sort of closer towards sort of the hump, and then the median is going to fall somewhere in between the mean and the mode on these. Okay. Kurtosis, remember, this is describing the peaks and the tails of your distribution. Positive kurtosis, we're going to have heavier tails and a narrow peak. Okay, this is your sort of T distributions, most notably at low levels of degrees of freedom, are going to be notably leptokurtic. They're going to have positive kurtosis. Negative kurtosis, you got a flat center, heavy shoulders. This is your like square distributions, right? Or things that are pretty domed, right? I kind of got everything. I just captured everything like kind of right in the center, and I'm not getting much on the tails. Okay. Recall that both are whether or not I have positive kurtosis or negative kurtosis. So the potential impact of this is we're underestimating variance. Okay. Doesn't matter whether or not I'm positive kurtotic or negative kurtotic distributions. The concern is underestimating your population variance, which we then need to sort of be addressed with larger samples. Okay. So again, if I'm not getting full representation of my variability, if I'm running quality of variance tests, I start to worry that those are sort of good or telling me the right things because I'm actually not sampling the full variability. We can also start to see impacts on bias, parameter estimates, standard errors. If the variability of my data is low, what's going to happen to my standard error? What do you think, Charlotte? If the variability of my data, if I'm underestimating variability in my data, what's that going to do to my standard error? It's what?
Yeah, I said, sorry, I was just, if you're underestimating it, then you're standard error gets smaller.
Yep, my standard error is gonna be too low, and if my standard error is too low, what happens to my inference tests? Like my t-tests and my tests of my coefficients and stuff. If your standard error is too small, where does the standard error go in like a t-test equation? Denominator. If my denominator is too small, what happens to my output?
It's getting bigger.
It gets too big, right? So what I'm gonna do is I'm gonna overestimate, my p-value is gonna be too big. Because I've underestimated variability in my data. My standard errors are too small. My standard errors are too small. My test statistics and my hypothesis tests are gonna be too liberal. So I'm gonna be finding effects where maybe I shouldn't be finding effects, right? I'm gonna make more type 1 errors, right? So again, this starts to become important in thinking about not only like just like, oh, hey, that looks weird, or that's not a perfect line. Think about what are the potential consequences of this stuff. Going through and taking a look at skew and kurtosis, again, not looking at p-values on skew and kurtosis, that's nonsense because I mean the assumption isn't that your data has a skew value of 0 and a kurtosis value of 2. It's just or a kurtosis value of 0. It's that they're just sort of within bounds of what we would expect, right? So and again, if I have a big enough sample, anything that deviates from 0 is going to pop up as statistically significant. So be wary anytime you're reading a paper and they're reporting a screening and they say we have significant skew. I got no clue what that means. That could mean you have a skew value of 4. It could mean you have a skew value of 0.2 and you just have enough people that popped up as significant, right? That has 0 meaning to me because the significance is just going to be completely driven by sample size. Like, I don't know if it's problematic or not. Be careful of that because it happens all the time. People are like, we had significant skew, so therefore we instituted transform. Well, I don't know if you needed to do that or not, or you just made everything a whole lot more complicated than you needed to, right? So being aware of that. Looking at the shapes of your distribution, absolute values of your skew and kurtosis value is going to be more informative. Again, general guideline is around 2. If you're under 2 for skew and kurtosis, you can generally say like, I wouldn't say that your data are normal. You just say that my data are sort of not demonstrating strong evidence of problematic deviations. Okay. Even after first semester, Jack, if you get a skew value of 1.9, does that look like a nice distribution? Does that look like it's approximating normality? No, it doesn't. It is very, very clearly skewed. Now, is it skewed to the point where we start to like freak out about stuff? Maybe not, right? But it's something that's notable, right? So again, sort of examples of just some of my own writing. Values of skew and kurtosis were acceptable, right? I'm not saying it's normal. I'm just saying like it's within bounds of what we typically allow, right? Saying that skew and kurtosis, they don't provide evidence of problematic deviations. There's ways of phrasing this that are representative of what we're actually seeing. Now, with skew kurtosis, you can start to get kurtotic distributions and things along those lines. I mean, there are, if I'm looking for a reference that says that it's okay, Klein's a great resource. This has to do with like SEM types of models. And if you got a large enough sample, kurtosis is probably not sort of that terrible of a deal, right? If you get a big enough sample, you're probably going to get sort of get a better estimation of the full range of variability. But just something you want to go through and be mindful of. What I don't want to see in your screen, so long as you get a kurtosis value of less than 8, then you're like, nah, it's good, right? So just want to keep. This is an example of an argument that can be made that might not be a very strong argument, right? Just because I can't argue for something, it doesn't mean that anybody should agree with me. I mean, it's an argument that I've made in papers before, but with some basis. But still, honestly, if I'm sort of a straight face, like, yeah, it's pretty kurtotic. That distribution is not doing what I would like it to do, but I'm probably not going to pull the plug on a full study just because I got one variable that's sort of giving me some nasty kurtosis, right? So just wanting to think about like, what do we do with this? How do we describe it in a way that's defensible, but then also sort of making sure we're taking into consideration potential impacts. All right. Yeah, histogram's gonna be sort of super helpful. So the only caveat there is what histograms look like depend on how you go through and bin things. For the most part, sort of SPSS does a good job of going through and binning, but this is why we go through, and I have you go through and look at box plots too, because that's just a formula. Box plots that features each component of your box plot means something specific. And that's gonna be more uniform against, across programs versus your histogram. I can screw around with a histogram until I can kind of make it look better or worse, depending on how I go through and bin stuff. Which is why, so we want to sort of put those, box plots in there as well. All right, questions? There's a lot of this is all just recap from last semester. Kind of sticking, sort of making some sense, things along those lines. Okay. Quick note on group-based analysis. We generally assume that our group-based designs, our t-tests, our ANOVAs, things along those lines, going to be pretty robust, particularly within relatively large samples. We got simulation research, like you got 25 people per cell. You can handle some kind of nasty distributions with that. Now, I would not say 25 per cell isn't necessarily a large sample. Katie agrees with me. So, but I mean, like, here's the thing, like if you're doing group-based analysis, you start to get like 40, 50 people per cell. That starts to be sort of pretty good, right? And also a lot of this also kind of depends on what you're actually measuring, what the scale is, right? If you've got a 1 to 8 ordinal scale, there's only so far out of bounds people can be with that. And if you get a decent enough sample, you handle that. If you're getting something that's more continuous and people can be like 8 standard deviations away from the mean, then you got to sort of be a little bit more careful with that. But it's also sort of important to remember that there are situations where, and this is going back to sort of stuff from the 60s, right? When we should start to become calling into question sort of the validity of our inferences in situations where we start doubling down on violations, right? So if I've got group-based analysis where I've got different shape and different variants, right? One I can handle, put them together. I start to worry about sort of the potential impact that's going to have on stuff, right? If I've got, Charlotte, you got condition A that's pointing sort of strong negative skew, condition B, strong positive skew. And this one is pretty tight. This one is sort of way stretched out. Even if you got a decent size, even if you have 25 people per cell, I'm starting to worry about sort of what that's going to do to your results. Okay. Different sample sizes and different variants. Here we can start to predict the potential impact on our tests, right? If I've got the bigger sample, you know, I've got 20 people in this sample and in this cell and 200 in the other one. And the one with 200 has way more variability. That overall ANOVA is going to give way more weight to that one. And then sort of my standard errors are probably going to be too big, which is going to make my t-tests or my inference tests too overly conservative because my group with the 200 people is sort of getting to sort of have how much say sort of the overall estimation of variability, right? But if my sort of big sample has the smaller amount of variability, then I'm probably underestimating the overall variance in that mean squared error, which is going to reduce my standard error. It's going to make my test too liberal, right? So we can start to think about the potential impacts of our violations and think about what the potential consequences are for p-values and inference and things along these lines. Small sample sizes, violations of normality, right? So again, going back to last semester, thinking about like for our group-based analyses, tend to be pretty robust, can handle most things. But if I start doubling down on specific types of violations, it can start to have consequences for sort of the conclusions that I'm drawing from my tests. All right. How are we doing? We're moving through stuff pretty quickly, but hopefully a lot of this is just review from last semester. Okay. Extreme values. Okay. Univariate outlier. An extreme value on a given variable. We already know about that. We've talked a lot about univariate outliers. What we're going to introduce this spring is the concept of our multivariate outlier, okay? Multivariate outlier is a case that has an odd configuration of scores, right? There is something in combination about this case that starts to make it different categorically from the rest of the sample, okay? So let's say I'm doing some demographic sort of econometric types of things, and I'm interested in looking at the combination of age, income, and sort of geographical region on something, right? Let's say we're looking at, let's say this is one of Scott Frank's studies. We're looking at some sort of implicit bias or sort of like something along those lines, right? Across each one of these, I can have someone who's 10 years old in my study. Are there people in the country who are 10? Is being 10 a weird thing? No, being 10 is not a weird thing, right? I can have someone earning $130,000, right? Is that a weird thing? No, people earn $130,000. I can have people residing in sort of the world's rural South. Does the rural South exist in the United States? It sure does, right? These things individually are not strange. They're not going to flag as a problem, right? But if I go through and I find somebody who is the combination of all of these things, now all of a sudden I've got a case that's strange, right? If I have a 10-year-old making over $100,000 in the rural South, that's an atypical case. That's a weird thing, right? And so what we need to do is we need to start thinking about how do we go through and detect these things, because individually, I'm going to look at my distribution, everything's looking fine. When you get a case like this or a couple of these can really start to throw off your analyses in weird ways that are not predictable, okay? And so this is where it starts to become important to screen our multivariate outliers. So we're finding extreme values. First thing you want to do is make sure the data was entered correctly, right? Honestly, and this is the majority of the time, someone miskeyed something in or accidentally, my cat stepped on the keyboard and it changed the value or something. Always want to go through and sort of also a good plug for having good records. Always have sort of organized, if you got hard copies of stuff, right? Hand filled out questionnaires, make sure you know where those are, go through and check, right? So in our lab, we're doing interviews and stuff like that. We can always go back through, pull the file and say, all right, yeah, someone just entered this wrong, right? If you're doing all online data collection, there's less worry about entry, but there we want to make sure that there wasn't like a data set that I accidentally jimmied with for something else and then forgot about it, and then it got that included over, right? Always having that original data set intact that you can go back through. Here's my archived set that no one gets to touch. Anything else I do, anything I do off of that is a copy of that original so that I can always go back through and reference that. In programs like SPSS, sometimes we just entered a missing data code, just forgot to tell the program to do that, right? So it's reading something as literally 999, but that's obviously not a real thing, right? Those will pop up on your Z-scores and your histogram. You'll have like one bar and then something hanging way out there that this may have happened to you last semester. In fact, that doesn't look right. Oh, I need to go through and fix this, right? Other thing that can happen is that case is not an intended population, a member of the intended population of study, okay? I am interested in this specific group, right? Let's say, Charlotte, you're interested in looking at sort of neurodiverse individuals and some sort of outcome things along those lines. And you look at some sort of measure and you're finding something like way off based on stuff. And you go through and maybe it's sort of a nonverbal child who sort of got sort of included, like, well, that's actually sort of part of the population, not as part of the population that I'm specifically looking at. So this person is actually representative of someone who I want to include. And so having them in there messes with my generalizability. So we want to remove that person because they're not want to look at that, right? Here we can also have someone who's an intended member of the population, but they're just underestimated, right? Let's say, William, you're looking at like opiate use or something along those lines, and you are interested in the full range of opiate use among, let's say, undergrads, but you just happen to get one or two people who are heavy users, That doesn't mean that they're not relevant. They are actually representing the tail of the distribution you're interested in. It's just there's a huge gap between that person and anybody else, right? And so we got to think carefully about what do we do with that, right? How do we deal with not wanting to just cut them off because you're like getting rid of the people you actually are most interested in, maybe, but just leaving them in there on their own is going to go through and skew things badly, right? So we got to go through and think about how we handle this. Problem with extreme values is this can do all sorts of stuff. This is not a predictable thing that we can go through and deal back. Oh, I got violations of homogeneity, variance, and differences in sample size. I sort of kind of know what that's going to look like. This throws things all over the place. No way to know exactly how it's going to go through and impact things. Although we do know that it's going to reduce the generalizability of the situation because you got a couple of cases that are having undue influence on your results. And so I would not expect this solution to generalize in any other study anybody would do. And so that starts problematic. Okay. Thinking about identifying univariate outliers. One thing, please mark and star in your notes. Tend to think about this outliers as existing on continuous scales. We need to also look at our categorical data, our dichotomous indicators and things along those lines, and looking at representation balance, because we can have outliers in our categorical variables, dichotomous variables with uneven splits. This is something that came up a lot in providing comments on screeners for last semester. Unbalanced designs are important to sort of note, but also not to overestimate the impact of, like, not everything is going to be sort of a nice sort of RCT or a randomly assigned sort of grouping. We've got quite a bit of play. Like, what we note as big, hey, this is a feature versus, hey, this is a feature that's causing problems and maybe undermining inference, is 9-to-1 difference is pretty big, right? Now, is it optimal to be like sort of 2-to-1, 3-to-1? Maybe not. Is it a reason to like throw the whole thing away? Probably not. They got to get up there. But what starts to happen a lot of times, and when we start to see this, is when people start asking important questions about representation and sort of what things might look like in different groups and things like that. And I've got, 90 white non-Hispanic folks in my sample and 5 people of color or something like that. And then I'm trying to infer something about, like, that's, you don't have enough information to do anything. You're actually probably doing worse by trying to separate that stuff out, because it's going to start throwing things off, right? So what we want to do is, sort of, if you're wanting to do that type of research on the front end, doing a good job of recruiting and sort of trying to specifically sample people are going to be not represented super well, and pull them in, as opposed to just hope for the best with what happens on the back end, because statistically you can create some problems with this. Okay. When you get extreme splits, we can attenuate associations. Things don't look like they're strong, or sort of we don't see relationships when there perhaps are some. Sort of any one person in that group of 5 or 6 has a far greater impact on the solution than any one person in the bigger sample, right? So we've got to be careful of that. And unless, if you've got those massive types of split, unless it's critical that you have that variable in your analyses, you should probably think about getting rid of it, right? Or it was essential to your analysis, you should have thought ahead and made sure that you got reasonable representation of that on the front end, right? So again, wanting to be careful about thinking about how we're specifying our model, what we're including, what we're not, and the potential consequences, because it's just not it's not just like a free for all. Just toss that in there, and if it works out, fine, or if it doesn't, whatever. It can actually start to screw with your model in ways that you might not anticipate. For our continuous variables, typically looking at z-scores. In general, reasonably large sample, thinking about Z's, 3.29 is kind of a reasonable cutoff for stuff. But again, remember that this isn't a bright line. This isn't a magic number. Like, this is just a reference point on a continuum that tends to correspond with this thing. And so, again, want to be very careful with how you're going through and describing stuff. Does this mean if you got a z-score of 3, that it's not a big deal? It might not be a big deal, but might be worth talking to. talking about. If you got a Z-score of 4, does that mean like that person necessarily for sure needs to be gone? No, depends on your sample size, depends on what you're measuring, right? And as you start to get large enough samples, you're gonna have extreme values. That's just telling you that you've sampled enough people to really start to grab those extremes, right? But the nice thing is if you've got a sample of that size, you're getting sort of the ends of the distribution, but you can have those people without it screwing anything up because you've got enough representation across the full dimension, right? So again, I would say when we're thinking about how are we conceptualizing extreme values, at least in the univariate sense, I'm more sensitive to where this is landing relative to the rest of the distribution, maybe more so than the absolute value. Now, the absolute value, like if you got something that's 7 standard deviations for the mean, you got to sell a sample of like 25. That's obviously something that's problematic, right? I think sort of, but in sort of the applied cases, the bigger issue is like, no, I kind of got this distribution here, and then I got a pretty big gap, and then a couple other people hanging out here, right? That to me is maybe not something I need to mess with statistically. It might be fine to just have that. But for me, it's more important to note that like, hey, we kind of got to the top of the scale and then I had some space and then we got some people popping up. Who are those people? Who do they represent? And what does this mean in terms of inference and who I'm looking at, who I've captured, things along those lines. Okay. Questions about this? Okay. Univariate outliers, so looking at your box plots. So this is just working through kind of what's your box plot. Anybody confused about box plots? Hopefully we're good on box plots. Everybody know what the different pieces of box plots mean? Okay, good. Make sure you know. It'll come up. Okay. All right. How do we address univariate outliers? Made a mistake, fix it. If someone is, you got a screwball in there, this will happen. Like, so, and this is where it's nice to go through and to keep good notes, right? Make sure that your RAs are got eyes on people as they're going through and running your experiments, right, Katie? Like, if someone's doing weird stuff, make sure that they're writing it down. Did I tell you about the guy who's running a study up in the lab, took his pants off? Yeah, right. Big person took their pants off. So I'm like, I don't know that we have to throw this guy's data out because he took his pants off. But like, if I'm going through and I'm running my screening, and I find someone's hanging out in sort of in weird space, and then I go through and pull the file back. Oh, that's the dude that took his pants off. All right, like this is maybe someone who wasn't sort of fully committed and paying attention to what he was supposed to be doing. So I'm fine to go through and remove this, right? So keeping good records so you know who you're excluding and why, right? If the case isn't part of your population of interest, fine, just get rid of them. They're not sort of part of who you were looking for anyway, so that's fine. And then alternative procedures here. We did this a little bit last semester, doing some smoothing, okay? And some strong reactions to smoothing, and I agree, sort of like, it seems weird, like I can't remember, Kate, if that was you, if you were you skeptical of smoothing? Am I thinking about somebody else? I don't know. It's worth being skeptical about. Basically, we're saying like, hey, I don't like your value. It's too big. So I'm just gonna like assign you a new value that's 1 unit higher than sort of the next person in the case, right? It's a weird thing to do because I'm basically making up data, but it is a statistically acceptable principle to go through and try and bring people in, right? So, William, if you're looking at like opiate use in undergrads, I can't have that person hanging way out there and run my analysis because it's going to mess with stuff. What I'm going to do is I'm going to document carefully that I had these 2 cases or 3 cases. What I did is I brought them back in line and set them sort of 1, 2, 3 in order next to sort of the next highest case, recognizing that I've done this, and then we're kind of sort of taking things from there. Yeah.
It's like Windsorizing a smoothing procedure, like everything outside of 3 steps.
Windsorizing is the problem that we have in clinical land is that like if you're windsorizing, you're often like getting rid of the people who are most interesting to you, because what you did with windsorizing, you just like drop those cases, right? And this is the other thing too. Windsorizing, if you don't not familiar, Windsorizing is a process where you're saying, what I'm gonna do with my data is I'm gonna get rid of the top, let's say 5% on the high end, 5% on the low end to sort of kind of bring in and sort of kind of cut off those tails, okay? And in certain sort of biostats and things along those lines is something that is sometimes done. You don't see this too much in psychological science. One, because depending on how aggressive you are with your Windsorizing, you're dropping your sample size. We always struggle with low sample sizes anyway, and so if you're just cutting them off, then you lose those. Now, if you're running sort of medical data and you got a database of 400,000 people, losing the top sort of 5% on either side isn't going to hurt you any because you got plenty of people there, right? But for smaller scale stuff, we start to sort of worry about it. The other thing too is thinking conceptually, what am I doing, right? A lot of times we are interested in some of those most extreme cases, right? But you would want to have a strong reason for saying, like, no, the focus of my research is really on what's going on and sort of kind of the normal part of the distribution, what's going on in the body, right? And there are reasons to make this argument. These are the folks that are most representative of the population I'm trying to get at. And so we're going to look at what's going on there. People outside of this have something different going on, so I'm just going to cut them off. Or if you have questions about your assessment instrument, right? So the concern is that anybody's fallen way out there. I don't know if that's real or those are valid measurements because we're pushing the boundaries of my assessment protocol once we get to those, and so we're just not gonna sort of include that, right? For those of you just coming out of Tara's class, you can think about people on the very high and low end of like IQ testing. You know that our measures start to get less reliable towards the end, and there's those confidence bounds around those point estimates start to get pretty big, right? So you may say, like, I am okay losing my super geniuses and my folks maybe with profound intellectual disabilities and cutting them off and just sort of focusing on this, right? Like anything else, if across the course of your career you just have a good reason for doing something that you can verbalize why you've done it, I'm going to be super happy and proud of you. So I would say just having a good reason, thinking about like what am I doing and what are the consequences, and sort of forwarding an argument for why this is an acceptable thing to do. Not everybody has to agree with you, but at least having thought through why you would do that, right? So William, to your question, Windsorizing is something you don't see so much here, right? But is a very valid statistical sort of procedure and a way to get rid of some of this stuff. You would just want to have a good conceptual reason for this is what I did, these are the consequences of it, and I'm fine with that. Makes some sense.
Yeah, okay.
The other thing too with smoothing, where you might want to consider smoothing, is in cases where your actual distribution isn't too bad, right? If I had a reasonable distribution of it, you would get this for opiate use, but let's say I'm looking at inattentiveness or something like that, right? Where I have kind of a reasonable distribution, but I've got a couple people who are way here high at the end. I don't necessarily want to transform my whole distribution to try and pull in 2 cases or 3 cases that are sort of high on the thing, right? Because as soon as I transform that, messes with my interpretations. And so I want to be careful with that. So I don't want to change the whole distribution and put that on a whole different nonlinear scale just to pull in these other people or this handful of cases. And so here's maybe where I would choose a smoothing procedure over a transform. Now, in sort of the case that we're talking about with sort of opiate use in university undergrads, I would hope that that's a very skewed distribution. And if you have some people who are way out there on the end, a transform might make more sense in that situation. But again, it's one of these things you have to think carefully about, like what's my data doing and what's going to make the most sense. Questions? All right. And then transform. We're going to talk about transforming. Critical. if you've got problems with your univariate distributions, you need to address those before you get into looking at multivariate outliers, multivariate screeners, okay? Because if you don't, what's gonna happen is you're gonna get a bunch of stuff that gets flagged as multivariate outliers that are a direct function of your weird univariate distribution, stuff like that, okay? You just waste a bunch of time because all the cases that came up as problematic in your univariate distributions are gonna come up as problematic in multivariate space. You gotta get your distributions in order before you sort of go on to that next piece of things. Okay. All right, thinking about some transformation stuff. Okay. This is a tricky thing for me. Okay. And I think we can think about this in terms of data-driven versus theory-driven analysis. Okay. There are some areas, and again, so I keep going back and picking on William, but it's just the nature of the stuff, like substance use and things along those lines. Transforming very common. It's just like you're going to see them all the time, and it's not a weird thing because everybody transforms their data because it's just a distribution that needs to be transformed to be sort of reasonably sort of managed with stuff. Okay. The drawback of transformation is it's going to go through and it's going to complicate interpretation. Okay. When I started, I'm no longer looking at the relation between extroversion and problematic alcohol use. I'm looking at the relation between extroversion and the log transform of problematic alcohol use. Okay. I know what problematic alcohol use looks like if I'm measuring this in terms of number of drinks. I have a harder time understanding what the log transform of number of drinks is. Like I went from dollars to the log transform of dollars. Dollars, I know what to make in dollars, right? The log transform of dollars, I don't know what that. I have a harder time understanding what that is. The sin is what people will do is they'll go through and they'll implement these transforms and then pretend like they didn't do it, right? Like I went through a log transformed motivation, and then I'm still talking about it, and then I like forget about it. I act like I'm just using sort of the standard scale when you're not, right? You're using a very, very different metric, and those things mean different things. And so if you would like to go through and transform your data, my argument is that it's now the burden's on you to go through and accommodate that and think carefully about what that means in terms of your inference and what you're actually looking at. And the problem is there's a lot of really cool stuff and really meaningful, interesting stuff that's going on that we just ignore because we don't want to deal with the fact that I transformed it and it's just a transform variable. There's actually critical things happening in terms of what you're assuming about the nature of that relation that probably need to be discussed, thought about. Okay. So again, what you would want to do if you decide to transform your data, just have a strong justification for it. The thing that I see a lot is like, oh, I have significant skew, and so I transform my data. Like Christ, like what does significant skew mean? Like what did you just had a p-value? Like I had a p-value of 0.04 on my skew when I have like 500 people in my sample. Like you just messed stuff up. Like you didn't need to do that. And now you've got an outcome that was nice and interpretable, and now I don't know what it means when you never needed to do that in the first place, right? So just warn you to think carefully about what is your justification for transformation, okay? Tabasco and Fidel support pretty liberal use from a data-based approach, right? And it's a tool that we should have in our pocket and know that we can use. I would just say sort of because there are such sort of big impacts on interpretation and what this actually means in terms of inferring things about human behavior, my preference is to think about like, what other options do I have available to me before I pull the trigger on this, right? Now, again, if you're in an area where if you, William, start reporting untransformed audit scores and every other paper has transformed those audit scores, you're going to look weird and people will want to know why you didn't. And sort of arguably there, you're like sort of producing research that's not consistent, compatible with existing stuff because everybody else is doing it. Then we're kind of in a different situation, right? I'm talking about the situation where Catherine, you're on your thesis, you got a regression model, be like, oh, I didn't quite like the distribution of that. So I just like square root transform something. And now you're talking about the square root transform of something. I don't know what that means, right? And it starts to become problematic in thinking about like how we go through it and make interpretations. Okay. In terms of common transformations, a lot of this is just trial and error, right? Now sometimes there will be, your natural log transform. This is awesome. If you do have to transform your data and can use a natural log transform to bring things in line, that's great because there are some cool things that natural log transform does in terms of retaining interpretive stuff. Okay. But a lot of this is just trying to go through and figure out like what nonlinear transform can I apply to my data to try and get it into a shape that is amenable to sort of running the types of analyses that I'm doing, right? So we've got the square root of your outcome. You've got the natural log of your outcome. If you got zero values, you can't take the natural log of a zero. It's going to sort of come up as nothing, right? So here, what you need to do, you need to take the natural log of whatever your variable is plus a constant, right? So most of this is just going to be if you have zero, it's just going to be your variable plus one, and then take the natural log of that. That way, it just removes all the zeros from your data, so you don't come up with missing values. If you have severe positive skew, you can do an inverse transformation. This is just one divided by the value. That will sort of do some corrections there. If you have, again, but same thing here, right? Need to be thinking about, do I have zeros in my sort of transform variable? Because I can't take one divided by zero, because again, it's not going to calculate anything from that. So again, we got to add a constant to make sure we're just shifting everything up, right? Someone will do this. Start it so that you don't, okay? All of these transforms are assuming that you have positive skew, okay? We're having skew where the tail is going in the positive direction. If you have things that are negative skew, in order to address this, what we need to do is we need to go through and we need to reflect your data, okay? What we're doing with the reflection here is you're going to set some constant and subtract your actual score to just flip this distribution around, okay? Here, K, we've got a constant that's subtracted from each score such that the smallest value is 1. We're usually setting K equal to the largest score in the distribution plus 1, okay? So I've got, let's say, negative skew on a 0 to 100 score. What I'm going to do is I'm going to set K to 101 and then subtract sort of my actual value. And what that's going to do is it's going to reflect, right? So if I have a value of 1 on my 0 to 100 scale in this negative skew, and I have 101 and I subtract 1, Katie, what do I get for my reflected score from that person? 100. Does 100 represent on their reflected variable? Does 100 represent a lot of my value or very, very little of my value?
What was the context again?
So you've got a 1 to 100 scale, right? And you've got someone who's got a score of 1. So they're at the bottom of the distribution. So I take 101, subtract 1, what do I get? 100. So that now that value of 100, now that represents what?
Choices I had. A lot.
A lot or a little?
A lot.
A little, right? Because again, the true value of that person was 1, right? And so that they're at the bottom of the end of the scale, but on my reflected variable, that person who had previously a value of 1 on the scale now has a value of 100, right? And if someone had a value of 100, right? So I got 101 minus 100, what do I get? 1, right? So what we do on this reflection, now high scores on my reflected scale represent low values of my construct. Low scores represent high constructs. But what I got to do is I got to flip this around, and then on my reflected variable, now I can start running square root, natural logs, inverse transforms, and things along those lines. What will happen if you try and transform a negative, use one like a log transform on a negatively skewed variable? It'll make the distribution worse, right? So what you got to do is you got to reflect it, flip it around, then go through, run the natural log or run your transform on the reflected variable. But then when you're interpreting things, you need to, 1, keep track of the fact that 1, I transformed this, and 2, I reflect this. So now up is down and down is up. If I've got a negative coefficient, it's saying I got a positive relation with things. If I got a positive coefficient, I got a negative relationship with things. things start to get pretty heavy and tricky really fast, depending on what I'm doing with this, which is why we always need to have a good reason for going through and pulling the trigger on these transforms before you do it, and knowing what the impact is and knowing the consequences are for interpretation. Questions about this? Yeah, sure.
I think I'm probably assuming that we're about to talk about this, but how do you preserve any interpretability when you do all of these? Because I don't know,
Sometimes you don't, right?
Okay.
But I think sort of what that natural log is nice because it turns things into percentage change, which is interesting. Percentage change is not a linear scale, but it at least is something that I can wrap my head around. Okay. If I've got, let's say, an inverse transform or square root transform, or like there are exotic transforms that and it doesn't matter. Like at some point, right? Like, does it matter if I've got the square root of my x or some sort of wild nonlinear? No, at that point, like it really doesn't matter, right? It's just sort of thinking about what are the consequences, what does this mean for my actual sort of variable of interest. Okay. So when we're thinking about interpreting our transform data, this is sort of the outcome of what our results are corresponding to, at the very basic level, sort of recognize that if we're looking at like a regression or ungrouped data, what we're looking at is we're looking at associations with my transform variable. Okay. Again, William, you got log transformed audit scores, right? You're saying this is the association of sort of this particular drinking motive with the natural log transformed audit scores, right? That's a reason. That's a fine way to do it, and you're just repeating that because we're not talking about just straight audit scores. We're talking about a transfer of those, right? And sort of making sure that you're sort of cognizant and sort of making sure your reader remembers that, hey, we went through and we messed with the scale on this. Okay. If I'm looking at grouped data, what I'm technically looking at, Jack, if you're looking at t-tests between across, say, sex and neuroticism or something like that, sort of men and women identifying, and so looking at neuroticism, so neuroticism is skewed, so you went through and transformed that. So basically what we're doing is we're no longer looking at sort of differences in means across neuroticism, we're looking at median differences, okay? What's interesting to think about is we go through with our transform, what we're doing is we're changing the shape of our distribution, but not the order of our scores, okay? If you come in this distribution, Charlotte, Jack, William, Catherine, Katie, and that's the order, and I go through and transform your scores, you all are still in the same order, right? The shape of the distribution looks different, but the order remains the same. And so as a consequence, the mean of the raw distribution and the mean of the transform distribution are going to be different numbers, but the order is going to stay the same. You're retaining that. So William, if you are in the median of the distribution of the raw scores, you will continue to be at the median of the distribution in the transform scores. Okay. So when we're working with group level data with that, we're looking at differences in medians as opposed to differences in means. Okay. So again, here's some random distribution pulled off of Google, right? Where we're saying, okay, here's the skew, or we've got a skewed distribution. If I go through and transform this, the median of this distribution, which is probably right here, is going to be the same person here. Like the order isn't changing. We're just kind of bringing in that tail to give it a better distribution. Okay. For continuous analyses, okay, and this is where this starts to get into how do we interpret this, right, Charlotte? I think the thing that, and I think it's just laziness in a part of our field, right? Thinking about mathematically what I'm doing and what that means for the phenomena of interest. Let's say here I've got a correlation between X and Y. And Charlotte, what is the nature of the association between X and Y here?
Positive.
It's positive. Is it linear?
No.
No, it's curvilinear. It looks like I've got a nice kind of quadratic function kind of going on here, right? Which means that at first, as at the low end of X, as X increases, Jack, what's the corresponding impact on Y?
Y increases
Increases by a lot or a little?
exponentially.
Well, at the low end, if we're like just looking down here, as X increases, does Y increase much? No. But as we start to get farther and farther along that X axis, what happens? My corresponding increases in Y.
Increases.
It increases more and more and more and jumps up exponentially, right? This goes through and starts to suggest something very different about the nature of the relation between X and Y than just a straight line, right? But what we go through and we do is we say, well, I don't like that. That a line isn't going to be a great fit for that. So what I'm going to do is I'm going to take the square root of Y and plug that in my regression equation. Okay. And if I do this, Charlotte, what about this this association here?
It's a little bit more linear. I mean, you still have
Yeah.
like a tiny curve, but
I got a little bit of curve there, right? But like what I did is I just transformed that. And now here, this is a representation of my relation between X and the square root or Y. And the line fits very nicely with that, right? My problem is, my beef with this is that what I will now likely do in my paper is talk about like, oh, this is the relation between X and the square root of Y and it's linear, and this is the relation, blah, 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 this, that, and the other thing, right? What's actually going on? And I've got something really kind of interesting about sort of looking at how changes in X covary with changes in Y that are probably kind of important, right? And if I'm not thinking carefully about what I've done with this method and I'm just applying it, sort of not thinking carefully through, there's a whole like Y as we start to get higher and higher in X, does Y start to jump up by bigger and bigger amounts, right? This is suggesting a nonlinearity between these two constructs that sort of does theory account for that? And if not, can we start to think about reasons why or how we might change this theory to help us sort of understand at a deeper level kind of what's happening here versus just like, oh, I linearized it and sort of then it made sense for my model and this is convenient. And now I'm just talking about X and Y as if they're sort of just a standard correlation when the actual underlying phenomenon, this is making a very strong, is sort of giving you a very sort of specific assumption about the nature in which X and Y are related that you can ignore and probably no one will call you out on that. But it's very much just by the sheer fact of transforming that with a nonlinear transform. Anytime you look at a relation with a transform variable, you are by definition making a statement about a nonlinear association, which I think is really exciting and interesting, right? But we often sort of aren't held to task to go through and actually account for why that might be. When I think that's actually something that's really kind of, we go through and force everything to be linear because that's what fits in our models, right? We have tools that do a good job of accounting for linear relationships and don't do a good job of accounting for nonlinearities. But if we just ignore the possibility that not everything might be related to one another in a straight line, I think we're missing big, kind of interesting big picture stuff about human behavior and things along those lines. So what I would say, as we're going through and we're working on sort of getting things in line to sort of go through and sort of fit into our regression model, would encourage you to think about the consequences of this, right? Like now, here's the tool I have, and I got to do some stuff to make sure that the data are amenable to the tool that I have. But then also thinking about what are the conceptual implications of doing this, right? This isn't a nuisance thing. It's actually implying something about the underlying relation between your variables. And so wanting to take that into account as you're sort of going through it and sort of thinking about like, what am I actually seeing in this? All right. Soapbox done. We're ready for a break. Any questions on transforms before we cut off? All right, cool. Go ahead, take 10. We'll jump back in with multivariate outlier stuff. All right. So, got transforms out of the way. Let's talk about multivariate outliers now. When we get into multivariate space, things start to get a little bit tricky, right, in terms of the visualization of things, but some concepts we want to be thinking about when we're thinking about indices of sort of metrics to identify multivariate outliers. One thing we use to talk about this is something known as a leverage. Okay, our leverage is going to be the index, sort of a number that gives us the distance of a case from the centroid for that individual to the remainder of the sample. Okay. And if we're talking about multivariate statistics, the centroid is just going to be the intersection of the means of all predictors in the analysis. Okay. Write this down, star this. If we're talking about multivariate outliers, we're completely talking about predictor space. Okay. Y's don't have anything to do with this. We're just talking about sort of configurations in predictor space. So let's say I have the centroid. Let's say I'm looking at, and so this is just would be a bivariate, a two predictor space here. I'm looking at the combination of weight and height on some outcome. Okay, and here is the weight. We've got the mean height is, about 68 inches. The mean weight, we'll say 180. This is sort of the mean of everybody in the sample. This is my centroid. Okay, and so here I have someone who exists as a multivariate outlier, someone who is 60 inches and 220 pounds. Okay, Catherine, what's happening? Like, what is going on with this case in terms of being a multivariate outlier? Why is this an odd case?
Combination of the two together makes it outlier.
Yeah, right. So we have someone who's 220 pounds, which is probably within our range. And we've got someone who's 60 inches, who's probably within range. But we've got a combination of someone who's noticeably lower than average in height and higher than average in weight, which sets them at a space that's different from here. Okay. And so our leverage is going to be the distance of this case from the centroid. Okay. And that's how we're going to go through and start identifying sort of multivariate outliers in multivariate space. Okay. Yeah.
How do we identify the outliers? Like, is it through like the Z, like 3.29?
There's specific stuff that we're going to get when we go through and call up our screening information in the regression. We'll get indices of these and we'll go through and look at them and describe them. Okay. So again, let's say I go through and sort of throw in, so this is two predictor space. Let's throw in a third variable. Okay. Katie, let's say I've got someone who's 76 inches tall. So this was sort of a taller than average person. And weight 230, so someone who's higher than average, but I mean, just kind of on the line, right? What if we add sex, gender in there? Okay, what value here would, or if we're talking about just sex, like what's going to turn that into an immediate multivariate outlier?
You mean like what sex?
Yeah.
Probably female.
Yeah, right. If we go through and sort of here, if we're not measuring biological sex in this, right? And we get someone with these characteristics, they're high, but probably not a multivariate outlier, right? But as soon as we add in a third variable and flip that from male to female, you're just going to get like sort of maybe a collegiate athlete or someone like that who is sort of disproportionately very large for what we would expect, sort of giving that. And now all of a sudden this person is going to go through and be in a different spot in three-dimensional space. So again, say if we go through and again throw up sort of height and weight like this, everybody do this, right? And now we add a third variable, three-dimensional space out here. Here's where, sort of right here where that centroid is. And now we've got someone who's way out here on that third variable that's drawing that out. right? Now, as we get into sort of 4 predictors, 5, it starts to get weird, right? But this is essentially what's going on, right? So we're looking about a combination of predictors that start to sort of make this person unique within the context of our sample. Okay. So what we can do, Jack, is when we're going through and we're calling up our residuals and things along those lines, we'll ask it to sort of give us values for leverages and sort of some different statistics so we can go through and help us isolate some cases. But these leverage values aren't going to tell us why cases are statistically deviant. Okay. This is what we need to go through and do to start to figure out not only do I have a case that's a multivariate outlier, what specifically is making this case different than the rest of the sample. Okay. So again, everybody look me in the eyes. If you tell me you have multivariate outliers and you don't tell me what's making these cases multivariate outliers, you're going to lose points on your assignment, right? This is just such a critical piece of things. Good, you found it, but tell me why what's going on. Again, this starts to become sort of helping you make a determination on what you do with it. And then also thinking about, hey, I've got a group of people who tend to be different than the rest. Is this kind of a unique subset of the population that is not being reasonably accounted for in this model, right? There's just additional research stuff that sort of starts to spark interest with some of these, right? So identifying what variables are causing this case to be a multivariate outlier starts to become problematic because if it's the same variable that keeps coming up as some people keep getting flagged as multivariate outliers on this one specific variable, it might suggest that there's something weird going on in your assessment. Your assessment might not be doing what it's doing, or it's not working well for some people. Like let's say I've got sort of measure and it keeps popping up, and let's say sort of Charlotte, you're doing it's a neurodivergent individuals are consistently flagged as multivariate outliers on this thing. There might be something about that assessment that's working differently with that group because they're not different in terms of what I'm looking, but the way they're responding to this is a different thing. And so I might cue me and I need to be thinking carefully about how I'm going through and assessing things, right? So it can be diagnostic in terms of your assessment, can start to help with decisions on whether or not the person is probably is a part of your intent population, right? These are folks who are coming up who are in a different space than other people. And maybe this isn't someone who's part of the people I want to capture, right? And so I can go through and sort of make a reasoned determination on whether or not I retain or exclude this individual. And then again, here's my solution. Here's the data that I've collected. Here's my model that I've built. Who does this generalize to? This does a nice job of accounting for folks in this space, but here's a collection of people who it doesn't. Like this model is not doing a good job or predicting in the same way for this group of people as it is sort of these other folks. Who are these folks? What does that mean for sort of the research area of interest? Is this suggesting sort of a possible new avenue of research or study, or maybe I'm looking at sort of what specifically is going on with these folks? Okay, so there's just inherent value. Like if you treat this as a task to be completed in a box to be checked for this class, it's going to be miserable, right? But if you're thinking about like how do I translate this into sort of interesting research and ideas and thinking about my data, that's when ideas start to pop up. That's when you have your notebook writing down like, hey, I wonder about this, or what could be going on with this type of thing. They can be really, really fruitful. Okay. We're going to use a regression, sort of other types of analysis. We're going to like hijack regression to go through and help us identify what cases and what variables are causing cases to be flagged. And we'll go through those procedures and kind of talk about how we go through that. Okay. How do we address our multivariate outliers? Okay. What we're going to do is we're going to go through and identify number and magnitude of extreme cases. This is a situation where unless you are William taking like a winterized approach where you're just like, I'm just going to wholesale lop off anybody who looks weird and just be interested in the middle of the distribution, you're going to have cases that come up, right? And just because something exceeds a threshold for what might be sort of worth looking into doesn't mean that it's a problematic multivariate outlier, right? Cut scores, rules of thumb, and you'll see this, are gonna overestimate or over-identify cases as potentially problematic. All right. And if you just start going through and lopping people off, your sample size is gonna get really small. The other thing that you need to do with these types of screenings is it's iterative. Okay. So Catherine, you go through, run your analysis, look at your distributions, get into your multivariate stuff, find your multivariate outliers. You go through, you say, okay, these 3 cases are problematic. I don't like them. I go through, get rid of them. Are you done? Are you good to go through and proceed on to your analysis? No. Guess what you got to do? You got to go back through and run it again, because as soon as I go through and I cut these 3 cases, other cases that didn't flag before now might pop up, right? Before, we call this some suppression effects, right? Like I didn't, or sort of aliasing, right? Like I didn't see, like Charlotte was hanging out in the shadows, and when Jack and William were there, like you didn't really notice her, but as soon as Jack and William are gone, now all of a sudden Charlotte's popping up as problematic, right? And so what can happen is this can be iterative. You go through, you find the people back, oh, these are outliers, we go through, get rid of them. Now you got to go back through and do it again to see if anybody else is popping up, right? And what can happen if we're just saying like anything above this threshold, go through and get rid of, you're going to start to really winnow down your sample. And then one that has cost for power, but for me, that's a pain in the ass to try and explain to my readers in a credible way why I went through and just eliminated 25 people because they weren't perfect and didn't do exactly what I wanted them to, right? To me, that kind of feels like I got my thumb on the scale a little bit. Like I went through and threw people out until my data did the thing that I wanted it to do. And so that starts to become suspicious, and people should be suspicious because of that, right? And so again, what we're starting to do is sort of impact power, potential loss of generalization, things along these lines, okay? So again, more of this, we're going to talk about some different benchmarks and sort of things to go through and look at. But Jack, when you're looking at these plots, what I want you to be looking at is like, okay, here's a collection of 15 cases that exceed sort of this threshold. Well, which ones are the ones that are most problematic? Generally, what you'll find is like kind of people like hanging out, and then there's 2 or 3 cases that are like very clearly like flying red flags out there. And you're like, all right, of the cases that went through, these are the ones I'm going to focus on because these are the ones that look like they might be like the most problematic. Let me go through, explore these, keep these in mind. When you're doing this analysis, these types of analyses, you're basically just like, it's never going to be the case where you just run one thing and then you just make a decision on whether or not to kick somebody out or not. What you're going to do is you're going to be like, okay, I went through and ran this in my univariate stuff. Charlotte, I see you, you popped up. I'm going to put a little check next to you. Went through to the leverages. Oh, who popped up again? Charlotte did. Okay, going to do this other stuff. We're going to look at discrepancies. Charlotte's back. And so if you keep getting flagged over and over and over again, now I'm in a better place to say, like, this is a case that popped up on 7 different dimensions. We probably need to think about whether or not we want to keep this, right? Versus Katie, you pop up on sort of this one and here. Well, you have your uniquenesses, but maybe not someone I'm sort of super attending and focusing on versus the repeat offenders that keep coming up again and again and again and again. Okay. So, wanting to go through and keep track of what's going on is through this process. And again, the other thing we can do, you got to be careful with this. And there are people who have strong feelings about this, but I think I trust that people can be within reason responsible investigators. There's two schools of thought with this. One is here are my criteria. I'm going to work through anybody who exceeds this criteria. I'm just going to get lopped off. Once I've done that, that's my sample, and then I'm going to move forward and do stuff, right? Fine, right? The problem is you're probably going to go through and you're going to lose a lot of people that you didn't need to lose. You cut people you didn't have to. It's a very data-driven approach that can get you into trouble because there are a lot of reasons people might pop up on something that are not actually reasons to be concerned, right? The other approach is what I would sort of suggest judiciously is to go through and Jack, maybe you go through, you say, I got these 3 cases that are kind of questionable, that keep popping up as folks. Do I keep these person? Do I not? Let me run my analysis with and without these people. Okay. Does it make a difference whether they're in there or not? And if it doesn't, then those are strange cases, but they're strange cases that aren't impacting anything. I think it doesn't impact my outcome to a level that it warrants me. And so my tendency is to be like more inclusive, right? I don't like to be in there mucking around with stuff if I don't want to be, or if I don't have to be. And so if, yeah, I could throw these people out, or I just keeping them in. They seem to be reasonable. These seem to be real scores. They have an odd configuration. When I run the analysis with it without the proof, nothing really changes. So I'm just gonna leave them in there, right? The risk there is you going through and making decisions on whether or not you want to present your model, whether or not so someone is in and out. That's some p hacking stuff, and then that's obviously problematic. But if you've got sort of an effect that depends on whether you have Catherine in the sample or not, that's a no-brainer. You don't have Catherine in the sample because if you got a decent sample, whether or not Catherine is in the sample should not make a big difference. Like if the results of your model completely change, whether or not Catherine is in there or not, that's a very clear signal that Catherine should not be in that model, right? Because it completely changes things around. Where you start to get into problems where like so people start like it's like if Catherine's in the model, it's 0.049, and if Catherine's not in the model, it's 0.053. That's actually not a difference, although it sort of puts you across the line. Then people, then things start to get fuzzy, and you know. But again, I can't give you sort of this is the thing you need to do every single time. Like it just takes you thinking about what's happening, what am I doing, what are the impacts, and then making a reasonable, ethics, scientific, data-driven, and conceptual decision on what you want to do with this stuff. Okay, there's just a lot of art, and the decision you make could be argued with by other people. People like, I wouldn't have done that. Like, well, okay, well, you do your own research and do so, but I've at least laid out my arguments for what I've done and why, and this is the reason. And if I would do it, and it's also nice to be like, all right, I could have done it that way. If I do it that way, it doesn't make any difference anyway. So I just try to sort of be more inclusive than less. Make some sense with this? Okay, cool. So again, this is iterative. Once you go through, if you do decide to exclude some people because they're problematic, you got to go through, pull those out. Then we got to go back to not square one, right? But now I need to go back through and rerun my or my my leverages, my residuals to go through, make sure that because that can happen and it does, right? Like I've got these wild cases that are masking some other things, and once I get rid of these, then these other things start to pop up. You can end up doing a couple of different iterations of this before you get down to something. But again, my recommendation was to go through, run some stuff, and then run things with and without. If it doesn't change anything, just stop because this can be you kind of take this too far if you're not paying attention. All right. Touching on linearity assumptions. Pretty straightforward. We're just assuming a linear relation or the association between a variable, combination of variables represented a straight line. Okay. Looking at this primarily through our bivariate plots and thinking about theoretical conceptual knowledge of sort of potential nonlinearities to sort of think about like where we might start to have problems, right? Again, we've got this quartet here where you're seeing a straight line, the exact same regression line through all of these, but inferring or implying very, very different types of relations between these sets of variables, okay? Linearity critical for the assumption of multivariate normality, okay? Again, multivariate normality, we're assessing this indirectly, and we're going to go ahead and assume multivariate normality if we have each variable and all possible variable linear combinations are normally distributed, right? And we're assuming that this is going to happen if all of my individual variables have marginally normal distributions and all bivariate relations are linear and homoscedastic. If those two things sort of happen, I can assume that my data are reasonably consistent with the assumption of multivariate normality. Okay. but the linearity piece of this starts to become important, okay? What this ends up being is you looking at a lot of bivariate plots in your data to go through and say, do I have anything that looks obviously non-normal in my data? Okay. Now, if you do find evidence of non-normality, some different things you can do with this, okay? One, you can transform, right? Talked about that before. You apply a transform and that can sort of make the relation between your predictor and your transform variable linear. And that's a statistical way to go through and address that situation. But there are other things that you can go through and do. You can dummy code, you go high-low, right? Could be looking at this right here, right? What I could do is I could say, here is, I'm gonna dummy code this, I'm gonna dummy code my X here. So I'm looking at low, high, right? And if I do that, if I take the average of low, I'm gonna get a point that goes right here. If I look at sort of the average of high, I'm gonna get a mean that's right there. It's gonna give me a line. Right, if I dummy code anything, the only model I can fit is a linear model. So I can't fit a nonlinear model. That can be problematic and there are risks for dichotomizing, but it is a way to address something, right? Do piecewise analyses, okay? Piecewise analyses, I have not sort of had much experience with these, but essentially what you're doing is you're building different models across different ranges of your data, right? So you could take this panel here and say that I'm going to have one model for X running -5 to 0 and a different model for X 0 to 5, right? Katie, if I do this, what's my model look like from X from -5 to 0? Yeah, I got a positive linear relation from X equals 0 to 5. What does that do? Negative linear relation, right? And so that actually does a reasonable job of, if you had data that looked specific to that parabola, like they would do a reasonable job of accounting for it, right? And the assumption would be that inverted U shape, sort of if you had a strong effect here and a strong effect here, right? So that's something you do. You can run nonlinear analyses, right? You can build in sort of different terms into your model that capture those nonlinearities. That's what Lucas and I did with that paper that we put together. Is we said, like, okay, I'm going to build in a quadratic term that's capturing the curvilinear relation here. Go through and do that. Other thing you can do, you just ignore it, right? And this starts to become, if you've got a situation, let's say something like this, right? Let's say you had more data that's kind of spread out. It looks like maybe there's a nonlinearity there, but I really don't have a reason to suspect that this variable and that variable would covary in any way other than a straight line. And a straight line would provide an okay fit to what we're seeing. Remember that anytime we go through and add nonlinear terms into our models, it makes it more complicated, okay? Which means interpretation starts to get a little bit more difficult. And nonlinearities are difficult enough to try and, anybody here make it to Calc 2? Okay. There you're talking about no, yeah. You're talking about sort of an acceleration slope and sort of different things like that, right? This is where sort of starting out as an engineer, I think it was kind of nice. I didn't make it sort of past Calc 2 because that's when I sort of kind of pulled the ripcord and got out of there. But starting to think about some of these things and sort of thinking about how this relation goes through and changes over the course of, right? You're talking about acceleration and changing rates and things along those lines. Starts to become interesting and sort of gives you language to go through and talk about that, but then you have to translate that for psychologists and sort of like kind of what this means. I'll post the paper that Lucas and I did for you to look at if you want to. I'm not going to sort of hold anybody to that, but just trying to say, like, how do you handle nonlinearities and how do you go through and talk about them? It's kind of a pain. Now, if you have a good theoretical reason for expecting that, then that's fine and kind of interesting. But if you don't, then it starts to become really complicated to go through and like think about, like, oh, how do I go through and talk about this, right? And so there may be situations where you just ignore that. And just straight line does a good enough job, at least at this stage of the game. I have no reason to suspect true nonlinearity in the population. So line fits okay, not perfect. In these data, I might fit a quadratic, but I don't know if that's gonna generalize anywhere else. So line's good enough, I'm just gonna ignore it. Questions on this? Okay. Variance assumptions, okay? When we're working with our group-based analyses, talk about homogeneity of variance, okay? And again, we're assuming that population variability on whatever it is I'm measuring is the same across sort of my two different groups of conditions, okay? When we get into our ungrouped data, it's the same thing, we just talk about it a little bit different, give it a different name. Here, what we're gonna talk about is our assumption within regression is an assumption of homoscedasticity, okay? What we're assuming, so with what we wanna see with a homoscedastic relationship is the variability in our scores for continuous variable y is the same across all values of x, okay? So if I'm going through and I'm looking at this panel right here, we're seeing that as I draw my regression line here, I've got relatively equal variability across this whole, right? So that I can't point to any value of x and see sort of large scale differences in terms of variability. Like, so at, let's call it the mean of x, here's variability in y. If I get at the low end, it's like slightly different, but it's not hugely different, right? Same thing here, right? This is a homoscedastic association. Down here, though, is what we would see with classic heteroscedasticity. At the low end of x, I have very little variability in y. Y doesn't change much, but as x increases, my variability in y starts to increase quite a bit, right? So if I'm looking at people who score low values of x, my outcome doesn't vary a whole lot. If I'm looking at the high end, we see things start to be spread out quite a bit. Okay. When we see heteroscedastic associations in our screening, it's often because it's associated with violations of univariate normality. If I have a skewed distribution, oftentimes that skewed variable will pop up and demonstrate what looks like heteroscedasticity in terms of that, in terms of the association with another variable, right? If I look at, like, sort of, for example, the association between income and age, okay? If I'm looking at people, what's legal working age, 15? You talk about 15 to 65, right? Why, Charlotte, might I see a heteroscedastic association between age and income if I'm looking at age ranging from 15 to 65?
Because when you're 15, you're probably not making that much money, but by 65, you've had a lot of time to establish a career, and like the amount of money that you could potentially gain exponentially was larger.
Yeah, right. And so there's just not much room to sort of deviate at 15, right? So, but as you sort of go through in the professionals, so lots of variability, right? So you would almost see something looking like this, if you were to look at that relation, right? And probably part of that has to do with skew in income, right? You have most people kind of down in this area, and then as you start to go through, you get that long tail. The people hanging out in the long tail, right? It'll be people who are older, right? And so you can start to see, if I don't address that problem with my univariate distribution first, I'm going to see heteroscedasticity oftentimes when I'm looking at my bivariate stuff. Okay. We can also see, though, variability in my measurement precision can start to produce heteroscedasticity as well, right? If I look at, again, I think some of the assessment stuff that you all did with Tara last year, and sort of think about cognitive achievement tests, that sort of reliability in the tails of that start to get less, right? And so what you might see, not maybe this, but if you're looking at the relation between like IQ and functioning, what you might see is a lot of variability on the real low end because they just don't have a lot of precision. And so then on the tall end, a lot of precision, and then sort of maybe it's kind of like an hourglass shape or something like that, right? Might be something that might be more characteristic if you have sort of things get a little bit loose as you get towards the ends of the scale, right? So we get something to be thinking about here. You will see sort of kind of what we're looking for visually in terms of heteroscedastic associations. So if we have violations of homoscedasticity, it's not the end of the world, but it does weaken our analyses, okay? For our regression models, and you'll see this happening time and time and time again, our parameter estimates remain unbiased, okay? So this means that our regression coefficients are unbiased. Sort of like, not saying that sort of like that I've actually hit the population value, but if I were to do all possible replications of this sample size that could be drawn from the population, the distribution of this coefficient that I'm estimating would center around the true population value. So the actual point estimate of your parameter is unbiased. But what happens is our standard errors can either become inflated or attenuated based on the characteristics of the data. Okay. And Jack, why do I care about my standard errors?
Because if your standard errors are different, your like T and P are gonna be affected.
That's right. With this whole system that we have with p-values, right? My standard error is the metric that I go through and use to test whether or not I have evidence for an effect. So my standard error becomes critical in my ability to have confidence in the decision that I'm making on whether I have evidence for an effect or not, right? And what happens if my variance decreases with a predictor, right? Like as X increases, variability gets smaller and smaller and smaller. What happens? My standard errors get too big, right? And then my test of that coefficient is going to be if my standard error is too big, what happens in my t-test, Charlotte? It's too small, and so it's more convert. I'm going to miss effects that I should be identifying. If it goes the opposite way, as my variability increases, as my predictor increases, so like we talked about with age and income, what's going to happen? It's going to attenuate my standard error. And then what's that going to do to my test? Make it too liberal, make too many type 1 errors because I'm going to identify things as different when they're actually errors, sort of as evidence of a unique association when I actually don't have one, right? So again, knowing kind of the impact of this starts to be critical, a critical part of that screening to think about what are the potential impacts of this as I go through if I were to just run this model. Okay. So again, looking at homoscedasticity through looking at plots of my observed data, my residuals. When we get into our multivariate, or excuse me, our repeated measures, ANOVA, stuff like that, we're going to fall back on a statistic known as F max. This is just going to be your variance across your largest and smallest cells. When we were doing just straight ANOVA and t-tests, we had Levine's test, right? There's a nice, gives us a p-value, made decision, equal variance is assumed or not. Multivariate or repeated measures, ANOVA doesn't give you one of those, or it will, but not for the repeated measures component of this. So what we're looking at is F max, right? To sort of say, do we have deviations that are sort of at the level that would cause us to have concerns, right? And if we got a balanced design, and sort of again, to put in perspective, statistically, we're talking about balanced design is a 4-to-1 ratio. It's pretty wild, right? This is like 100 to 25, right? That's a pretty big discrepancy. So we've got some tolerance. F max less than 10, probably fine-ish, right? Again, is it great? Am I excited about it? Probably not, but it's at least nothing I have to like hit the panic button on. But with an unbalanced design, I've got wildly different cells. F max bigger than 3 can start to reduce or produce greater type 1 error, right? So depending on sort of where that discrepancy falls with stuff. So again, wanting to go through and be careful in our screening, not only thinking about sort of do we have a problem? What's the magnitude of the problem? What are the potential consequences of this? All right. Solutions, transform stuff, right? If we have wildly skewed data or things that are not normal, we can transform, and that helps with stuff. We can also start to go through and look at different types of analyses that address violations of homogeneity variance. And here what we're talking about within regression models is using different estimators, right? Standard OLS is great so long as our residuals are homoscedastic. If they're not, it starts to weaken the analysis. And so there are different estimators that you can incorporate that do a better job of accounting for or not sort of having sort of the problems that can be introduced with problems with homogeneity or heteroscedasticity with stuff, right? They're it's fun, sandwich estimator, right? So weighted least squares, there's sort of different types of things that you can go through and use if you're finding that you have some of these problems. Okay. So again, another thing that you might go through and see now, like, hey, we're going to go through and do this. Like, do I want to transform every goddamn variable in my analysis to try and get it close to something that might approximate meeting my assumptions? Maybe not. Maybe I go through and I sort of do what I can and then say, then we switch over to a different estimator, give it some sort of uniquenesses about how these data are working together to better account for what's happening. Also, sort of other thing too, is if you know that the types of violations you're getting are going to produce more liberal tests, you can start to just tighten up your alpha levels, your bank. So here's the thing, and this would be like a big methods, like high standard moral like flex, right? You're like basically based on my screening, recognizing that the pattern of residuals that I'm seeing here could result in attenuated standard errors. As such, I'm going to set my alpha level for these tests to be equal to alpha 0.01, just to sort of give me a little bit more cushion, right? That would be a pretty impressive thing for you to do. You're basically saying I got one hand behind my back, sort of given that I know some biases, but so there's certain things that you can sort of go through and do with this. I've not done this, but with screening, sort of like, hey, sort of pattern I'm getting here. And this wasn't for regression, but it's like, basically I'm expecting my standard errors to be overestimated. And so my tests are going to be conservative. And then I had an effect that was kind of right on that border. I'm like, I'm going to go ahead and interpret this because I know sort of based on sort of my assessment of the screener that sort of my tests are going to be conservative anyway. So I'm going to give myself a little bit of grace on this 052 effect and still go through and interpret it, right? So thinking about how this can work for you in terms of sort of drawing inference and things along those lines, right? I mean, the better argument would have been like 052 and 049 is a different thing, but like people don't like that so much. So. All right. Questions? Okay. I think this is the last time we're going to sort of get at before we get into actual sort of residual stuff. But thinking about multicollinearity and singularity. Multicollinearity, we've got high correlations between variables. Variables correlated by 0.90 with one another, like from a statistical standpoint. Jack, with Casey, so you're doing a lot of work with constructs and things along. If I have two different constructs that are correlated 0.9 with one another, what do I have? Yeah, two measures of the same construct, right? I can't get two measures of PTSD to correlate 0.9 with one another. If I've got two things that are correlated at that level, it just means I'm measuring the same thing and calling it different stuff, right? If you get anywhere within like spitting distance of 0.9, right? You go through and you'll see like 0.8, 0.85 has been like sort of evidence of poor discriminant validity. Like you're already in poor discriminant validity if you're even sort of close to that sort of area. And so there's the difference between conceptually what I need to be concerned about and statistically what I need to be concerned about. Our regression models will handle and provide estimates for stuff like the correlation has to get really like 0.99 before things start to break down, right? But nothing in real life as we measure it in psychological science is actually correlated 0.99 with one another, right? So again, yes, here are benchmarks, but you got to think about like what that really means. Singularity, we've got variables that are redundant, linear combination of one another, right? William, if you go through and you have Williams measure of X and you've got subscale 1, subscale 2, subscale 3, and then a total score that's the sum of those three subscales, if you put subscale 1, subscale 2, subscale 3, and then also the total score as predictors of your out, it's gonna crash your regression model. It's not gonna estimate. You're gonna get a bunch of error messages and things along those lines, because you created a singularity in your data, right? And that's typically where that will start to occur. Okay. No count to anybody like linear algebra, matrix math, anything like that? Okay, so in my multivariate stat, we had to go through and like do matrix operations. So I had early on, and then I was like, this is taking up too much time. We probably can like sort of cut the matrix operations, still have people sort of have a reasonable understanding of stuff. But when we're thinking about sort of the math underlying regression, it's all matrix algebra sort of going on with stuff. What happens if I have collinearity in my data? I have redundant variables, okay? What I'm saying in my model, telling my model I have this many pieces of information. When I don't have that many pieces of information because they're redundant, I actually have this many pieces of information. What ends up happening within matrix algebra is you end up doing the equivalent of trying to divide something by 0, and you start to have problems and things start to go haywire, start to become very unstable. Okay. And so this is why we need to go through and take a look at stuff. So if we think about how we go through and detect collinearity, our bivariate correlation is the quickest and easiest way to go through and do it, right? You just pull up a correlation matrix, take a look at your associations, and see where things are at. Okay. Now, a couple of things to remember, like we've got situations where my model will start to do weird stuff if my variables are too highly correlated with one another, right? That's got to get really high in order to do that, right? Like you should start being concerned and thinking carefully about your model if you're anywhere sort of even halfway to some of that stuff. The bigger concern within from a conceptual standpoint, remember that what we want, our best, most efficient models are additive, right? So Katie, you're predicting some outcome here. You got this predictor that's catching this piece, and this predictor that's catching this piece, and this predictor that's catching this piece. Each one of everybody at the party's bringing something different. Everybody's contributing something, right? This is your best case scenario, reducing this and sort of increasing the power of your tests, right? What starts to become problematic with collinearity is I'm not doing that. I don't have a well-specified model. I've got, here's my outcome, and I've got this thing that I'm measuring, and then I've got my second variable that's doing this, and my third variable that's doing this, and my fourth variable that's doing this, right? Everybody just brought bean dip to the party, and now I got a party with like 7 plates of bean dip. Is everybody super happy about that? But no, it'd be nice if other people bring different stuff, right? No one's happy, and no one gets credited for bean dip because everybody got bean dip. So basically, no one brought anything, right? That's what's going on when we run into problems with sort of our multi-collinearity. So we've got, on one hand, we've got the mathematical like estimation piece of this, and then I would argue, so the bigger issue is, so I've got a poorly specified model. Someone just didn't think carefully about what they were doing. This is just like a, hey, here's a regression bin. I'm going to throw in whatever I got in there and see what happens. This is also the problem with stepwise or statistical regression, where we're just kind of throwing everything in there and seeing what happens. Okay. So we can go through and I can identify it like this. I'm going to catch this with just an assessment of my bivariate correlations. Okay. But collinearity can be tricky. Okay. And what we can get is multi-collinearity, where we go through, we start to find a situation where X1 is kind of correlated with X2, X2 is kind of correlated with X3, X3 is kind of correlated with X4. And none of these individually are correlated really strongly with one another. But if I take all 3 of these things combined, it almost perfectly predicts X4. And in that situation, you're not going to catch it in the bivariate stuff. You need some other tools to go through and see, like, where is that collinearity happening? Okay. And when we're looking at human behavior with imprecise measures that are not perfect, what we can do is be like, well, I went through and wanted to cover this, and this. Well, what can happen is as I go through and I count for all those, I also perfectly predict what's going on. this other thing, right? And so we need to have ways of going through and finding this, okay? What we typically see, in terms of our methods involve calculating our squared multiple correlation, our R squared of a predictor, regress on all the other predictors in the model. Okay, so I have X1 and I regress that on X2, 3, 4, and 5, right? Then X2, 3, 4, and 5 account for 99% of the variability in my outcome, then I got a problem, right? It suggests that there's redundancy across these predictors, okay? And this is what I would find there. If I have this variable and use all these other variables to predict that variable, the R squared on that sort of like mini side regression is going to be through the roof, suggests that I got way too much overlap there. Okay. Again, best case scenario in a regression model is I have orthogonal predictors, right? That they're all untouching and sort of getting at unique things. That never happens, which is fine, but this is the situation where we start to see some problems. Okay. So some different ways, statistically, we can see sort of values that go through and express this. Tolerance is just 1 minus your squared multiple correlation. Your tolerance value is just 1 minus the R squared of that variable regress on all that predictor, regress on all your other predictors. Tolerance values less than or equal to 0.1 are sort of thought of as indicative of problematic collinearity. Again, I asterisk this. If you get anything even close to a tolerance level of 0.1, it suggests that you didn't go through and think carefully about your model. You got problems with massive overlap, right? Again, in clinical land, this is like I'm measuring, I have depression as a predictor, and I also want to control for low self-esteem and neuroticism and the experiential avoid. Like it's all the same. Like you just measured the same thing 4 different times to control for it. Like it's everything stacked up on one another, right? We also have an alternative metric known as your variance inflation factor. This is just 1 divided by your tolerance. This is just a sort of a reverse metric on this, okay? What's interesting with your variance inflation factor, if you take the square root of your variance inflation factor, it's giving you a measure of the extent to which the variance of your coefficients is inflated as a result of collinearity, okay? This is getting at sort of the problem with collinearity in my model is it can start to make my standard errors very large and very unstable, okay? Your variance inflation factor is telling you, you take the square root of that, telling you like by how much, right? So again, if I had a BIF of 9, saying that the standard error of my coefficient for my target outcome is about 3 times what it would be if my BIF was 1, right? So it's kind of giving you you don't see people interpret it this way a lot, but it's kind of an interesting thing to sort of start to wrap your head around like how much of a problem this is. And again, if the standard error of my predictor is too big, what's that doing in my t-test? Dropping it down, right? And if my t-test is getting lower, I'm less likely to go through and find evidence for an effect. And maybe it's not that I don't have evidence for a unique association. Maybe it's just because I threw on 3 or 4 different versions of the same variable in there and it exploded my standard error. And so now I'm not finding anything. Okay. So again, VIF greater than or equal to 10, indicative of problematic collinearity. Again, if you're anywhere close to that, you need to be reevaluating what you put in your model and thinking carefully about what that means on a conceptual level. Okay. So again, most of our statistical programs require your tolerance to be within a certain threshold for inclusion in the solution. And that's anywhere from 0.01 to 0.001, right? Like, so your model will continue to estimate things way beyond the point that you should have concerns. So don't trust your model. I mean, your model is going to break down. Your model is going to give you something unless you've got like a literal singularity in there, then it's not going to do it, right? But know that this is all for OLS. If you're running regression models in OLS, it will still give you something. You should not be super trustworthy of what's coming on. But as soon as you sort of transition into like SEM space, yeah, maximum likelihood has no, like you'll get sort of undefined solutions and the whole thing will crash and you get all sorts of errors sort of with this. Things that you can estimate in OLS will not estimate in SEM. programs because of collinearity pretty quickly. This starts to get in if you start trying to estimate interactions and stuff like that. And we'll talk about when we get into moderation, so the benefits of centering and so what that does for stuff. So questions on collinearity? All right. Solutions. So I find that I have collinearity in my data. What do I do about this? Okay. Here's the thing. If my goal is just to predict an outcome, don't worry about it. Doesn't matter, right? William, what's the impact? What is the impact of collinearity on my tests? Where do I start to see problems with collinearity? What's it messing with?
Your interpretation,
Yeah, specifically through what mechanism? What's getting large and unstable?
standard error.
My standard error, right? But if I'm not interested in the unique effect of individual predictors on anything, if all I'm trying to do is maximize my R squared, who cares about my standard errors? I don't care because my parameter estimates are unbiased, right? And I'm not interested in my p-values for my individual predictors. If all I'm trying to do is maximize what's my revenue going to be like next quarter, here's like the 15,000 different things I plugged into my model, and all I want to do is maximize my R squared. Cool, don't worry about it. You're good to go. Okay. But this is often not to the type of research that we are doing. So we do have to become concerned with this. And so one thing we want to do is we want to check for data errors and proper coding, right? Make sure that I didn't code sort of one thing one way and the other thing the other way. It's actually indicating the same thing, and then everything kind of falls apart in my model. Okay. Here, wanting to make sure that my predictors in my model aren't versions of other predictors in my model. So I've talked about this, right? Scale total, scale 1 and scale 2. If I throw the three of those in all together, it's going to crash my model, because if I know what your value is for scale 1 and I know what your value is for scale 2, by definition, I know what the scale is for scale 3. I'm saying I have 3 predictors in my model. I don't. I actually have 2. It's basically the matrix version of trying to divide by 0, the whole thing crash, right? So watching that. Delete redundant variables. Think about like, what do I have in there? What's hanging together, and like, are those really different things, right? The answer is no. Answer the question, or at least in terms of how you measured things. And then it starts to become a question of like, conceptually, which one of these is most important, right? Psychometrically, which one of these is the better measure? Sort of going through and making decisions based on them. You can sum or average collinear variables. You know, let's say I've got 3 variables that I'm really interested in looking at, but they all hang pretty tightly with one another. You can sum or average those to go through and say, here's my composite variable for this. Should you do that? Probably not. They're just better ways to do that. Same thing, using a principal components analysis to create component scores to include predictors. This would be, I have 5 different variables. What I'm going to do is I'm going to submit this to a PCA and get a sort of a latent factor, and then sort of assign a score to that, and then use that score to go through and be the predictor in my regression model. This was a thing that was done at one point in our history. There's no longer any reason to do this. If that's what you're going to do, what should you just do instead? Just run an SEM. There's no reason to like create a variable that no one else can ever measure the same way and plug it into a regression model. Just model as a latent variable and just run it that way, right? So that's why sort of these two are things that sort of historically have been done, but like now there's really no reason to do that. You just run it in a latent environment and just kind of take it from there. Okay. All right. How are we feeling with stuff? Feeling okay? Likes my haiku. I like haikus. I think that's a pretty good one. This is a good stopping spot. So we'll go through and sort of put a pin in things here. What we're going to start with next week is we're going to get into our sort of actual regression assumptions. Start working through stuff. The problem set will be due Friday. What I will do before we get there though, is go through and just post your next set. Just so that you have that to work on. So this will be, for set 2, you're gonna go through and actually have data to work through. You're gonna start working through regression stuff and things along those lines. So, we still have a couple class periods to get through sort of this stuff probably. But I'm trying to think about how, with changes to the class, how to go through and navigate this. There are historically what I've done is gone through and like we go through and we run through, talk about like sort of different things and walk through kind of what things mean conceptually. And then, I've got sort of your typical, here's the data set, here's sort of the handouts, and kind of walk through them together in class and things, which is a nice way to do things, right? And it also takes up a bunch of time because someone can't find the right thing or someone clicked the wrong thing, and someone's sort of trying to figure out sort of what's going on. And so it's not, I think it's good, but it's not super efficient, right? Other thing we could do is we go through conceptually sort of everything, and then I have some videos of kind of the SPSS piece, the stepping through and sort of doing that part of things that we could spend class time saying, here's this portion of class for you to kind of go through and work on things together on your own, and have you watching those videos on sort of the nuts and bolts of how to get things out of SPSS sort of on your own, and sort of not sort of march through it in class. Do people have a preference on sort of recognizing that, like, I'm opening myself to being pilloried in evaluations regardless of what we do, but like, is there a general preference in terms of, I mean, it's nice to be able to talk through sort of live kind of as we're going through and doing stuff. And there's also benefits of just being like, here I'm at this point in the video and I'm just gonna stop and sort of make sure that my data, sort of think about, take some notes, and sort of do kind of my own pacing in terms of stuff. Strong preferences on how we would proceed with some of these. What's that?
Second option.
Doing it kind of just independently, sort of with the nuts and bolts and sort of stuff on your own.
Yeah, the class is fine to just work on.
Yeah, I also like the YouTube videos. Like if you, like when you usually put in like hour, 2 hours, minute, this section is necessary for this.
So some of those markers in there. Yeah. Okay. All right. Then becomes important for you all to go through and make sure that you are watching those videos at whatever level that you need to. Some people who have had sort of prior experience with regression stuff, like, okay, I kind of get this, so I'm going through a little bit quickly, but there's some tricky concepts, right? I will keep that in mind. So what we'll do is next class is we'll work through kind of conceptually, the slide, you can kind of see that this is what it looks like, this is what output looks like, that's how we go through and do it. But then what I'll do is I'll have data sets, handouts with all the instructions, and between the data sets, the handouts, the video, you can go through and work at whatever pace you want to go through and work through those to get a handle on kind of procedures and things along those lines, right? Which I think also is nice too, because otherwise you get, Catherine, you're sort of here and we've gone to the next step, but William, you sort of got lost in the wrong menu and you're trying to, now you're freaked out. And then Catherine's in your sort of computer trying to help you figure out where to show stuff. And I'm trying to talk through things, and it turns into a process a little bit. So, so long as people are comfortable with that, but recognizing that I am here and available to go through and talk through and work through all of that stuff. What we'll do, I think this will actually play out nicely. We'll reserve some class time for you all to kind of sit down and work through some stuff. But we won't spend the large amount of time sort of stepping through sort of moment by moment, which is basically the same thing that you would get on the video. So, okay, cool. Good. We will have that for our plan of action. So go through, wrap up problem set 1, get that in Friday at noon. Yeah. some thoughts just in sort of going through and sort of maybe, let's do this for, for this set. Let's go through and have like your write-up kind of as kind of that being its own thing. And then any appendices that you have that be a separate document. Okay, so you're gonna have a separate document that just has your appendices. It's gonna be like hand calculations, sort of the numerical. Do this, start with the numerical appendices. Like the first thing is just like, here are the numerical values for kind of the different things. So I can go through and check that. And then below that, say problem 1, any hand calculations, problem 2, sort of screenshots, whatever you got going on there. That'll be nice because on my giant monitor, I can have your actual write-up and then your appendices kind of side by side, and I can sort of do that. So does that sound all right? Okay, awesome. Well, our champions, thank you so much. And yeah, keep me posted on how things are going.
Thank you.
Thank you.
Or